Alright, this lesson is on improper integrals, and this will probably take a couple of videos, and if at any point you find that I am moving too quickly or you're just not quite getting the concept and I'm moving on, I strongly urge you to pause and go back and take a look at things and rewind and try to make sure you really get the concept of it. So go back and see what you can do. Okay, so improper integrals, kind of an interesting name. Um, excuse me. What we're going to consider is the integrals that have infinite limits or have some kind of an infinite discontinuity, another word for vertical asymptote, and what that means. So previously, we've only been able to integrate or evaluate a definite integral on a defined interval from a to b, which means that there were no discontinuities in between a and b. Well, now we're actually going to be able to take a look at and evaluate definite integrals in two new ways. The first case is what is called, where the interval is infinite. There we go. And the second one is when you have what is called an infinite discontinuity. Or, in other words, a vertical asymptote. Both of these are what are called improper integrals. And what I will tell you is that when we go through these, you're definitely going to have to understand the concept of limits. Um, and if you have not already learned what L'Hopital's rule is, that will come into play in a couple of these, at least one of them that I can think of towards the end. Um, so you might want to take a look at that if you're not familiar with L'Hopital's rule. I'll still try and kind of help remind you what the concept is there. All right, so let's get the concept of this down. So the type 1 is if we have an infinite interval. What the heck does that mean, an infinite interval? So if we take a look at the curve, y equals 1 over x squared, we're going to look at the area beneath the curve, and to the right of x equals 1 and to the left of x equals t. Well, first of all, in the first quadrant here, let's sketch 1 over x squared. It looks something like this. All right, x equals 1 would be right about here. Um, 1 over x squared would also basically be a mirror of this over here, but we're only interested in the positive portion of it for this particular case. So again, we're going to look at the integral, we're going to look at the curve and the area beneath the curve between x equals 1, which is right here, and x equals some value t. I don't care what the value of t is, we'll call t right here. And that would be right there. Now what you should see is that we should be able to integrate this whole area in here. Okay, that should not be a problem. It's a finite area. I'm going from 1 to some value t. I should be able to go ahead and take its antiderivative and do the integral and everything that we need to do to find the area. So if we did that, we can find the area of t by doing the integral from 1 to t of 1 over x squared dx. Remember that 1 over x squared is the same as x to the negative 2. So we can take this thing's antiderivative. That will give us negative 1 over x. So it would be x to the negative 1 divided by negative, so this is going to be negative 1 over x. And we'll evaluate that from 1 to t. And then if we plug in t, we'd get negative 1 over t minus, plugging in 1, we'd get negative 1. And we can kind of rewrite that. That minus minus becomes plus 1, so I can write the 1 out in front as 1 and then minus 1 over t. And that would be the area between 1 and t of 1 over x squared. Okay, hopefully there's nothing there that seems too outrageous to you. All right, we're going to carry that concept through. All right, so what you can say is no matter um, how large we choose for t, a of t is always going to be less than or equal to 1. How do I know that? Um, go back to this page. The bigger and bigger and bigger I let t be, doesn't matter how big it is, the closer and closer and closer this thing right here, because 1 over some huge large number is going to approach 0. So no matter how big I choose for this, the bigger I choose for this, no matter what, I'm going to do 1 minus some number. As long as t is greater than 1, this is no worse than 1. So no matter what, a of t, the area is always going to be less than 1. So if that's the case, it follows that we can say the limit as t approaches infinity of a of t equals the limit as t approaches infinity of 1 minus 1 over t, because that was the area of t. And like I just said, as t approaches infinity, if I plug really large numbers into here, this piece, this 1 over t, again, this is where your limits come into play, a constant over something which is growing really fast is going to approach 0. So this limit goes to 1. So the area of the shaded region approaches 1 as t approaches infinity. We could instead write the integral of an infinite region as the integral from 1 to infinity of 1 over x squared is the same thing as the limit as t approaches infinity of 1 over t of 1 over x squared dx, and we just said that this thing will approach 1. So let's kind of take a look at what that means. So again, if I took and I drew 1 over, oops, that's horrible. If I drew 1 over x squared, something like that, that's not very good, but you get the idea. Here's 1, and we'll say that this is 3. Well, if I were to go ahead and take the antiderivative and I plugged in 3 and I plugged in 1, we would get the area to be 1/3. Okay, and again, I could go back up to this thing right here and figure that out if I really wanted to. And then if I took and did it again, I know these drawings don't look very good, I apologize, and I went out to 5, well, now I can find this area, and the area of that would be 4/5. And as you can see, the further and further and further this goes out, the closer and closer and closer this value is going to become to 1. So let's talk about this notation up there. We cannot actually integrate something which is infinite, because technically an integration is a limit of the sum of rectangles. Well, if you have an infinite thing, then you actually can't take the infinite number of rectangles. But what you can do is we can let the integral go from 1 to t. T is a finite value. We can integrate something to a finite value, and then after we find this thing's integral, then we can take the limit as t approaches infinity, because now we're going to let that t approach an infinite number, and then we can figure out what the integral's value is going to be from that. So it's a very conceptual. All right, so on the next page is the definition of the improper integral type 1. And there's a lot of stuff here. I'm going to kind of highlight what you really need to know. So if you take an integral from a to infinity, so this is some kind of an infinite integral, and the integral exists for every number t is greater than or equal to a, then the integral is said to be the limit as as t approaches infinity from a to t. So basically you replace the infinity with a concrete variable. of f of x. And if this is a finite value, then the limit exists. I'm sorry, the integral exists. Wow, sorry. If for some reason you start at negative infinity and then you go to b, so we're just switching the ends of the infinities, then you replace the negative infinity with the t, and it's the same exact idea. If this limit exists for a or b, meaning you get a finite value, this is what is called convergent. It is telling you that the limit, I'm sorry, I keep saying the limit. If the integral, if the infinite integral here exists, if you get a finite value out of this, then it's what is called convergent. However, if you get something which does not exist, or you get infinity, which still technically means the limit doesn't exist, then it is called divergent. That is an extremely important concept. Convergent means that the integral actually gives you a finite value. Divergent means that it doesn't exist or goes to infinity. You can actually have the case where you have a negative infinity and a positive infinity as your bounds. We'll get to that. Okay, note, any improper integral of type 1 can be interpreted as an area provided that f is a positive function. Kind of an interesting statement there. So determine whether 1 over x dx, as the integral goes from 1 to infinity, is convergent or divergent. So the idea is, first of all, I can see that I have infinity in the bounds. We cannot take that as an integral, so we'll change that to t. So we're going to take the integral from 1 to t of 1 over x dx. However, at the end of this, because I do need that t to approach infinity, I need to take the limit as t approaches infinity. Okay, and this notation is very important. Without this limit, you're really not taking the proper integral. So we do need to have the limit. We need to change the infinity to a concrete variable. Typically, we use t. You can use other things. It just depends on what's in the problem. So we'll go ahead and take this. Now, you still work this just like you would do anything algebraically. You're going to work it inside out. So we're going to take the integral first, and then we'll take the limit at the end. So the antiderivative of 1 over x, of course, is the natural log. Oops, sorry. It's the natural log of absolute value of x from 1 to t. We are still taking the limit of this as t goes to infinity. That should be an arrow. Sorry, there you go. So now we plug in the upper bound and lower bound and subtract. So we get the limit as t approaches infinity of the natural log of the absolute value of t minus the natural log of the absolute value of 1. The natural log of the absolute value of 1 is just 0. So really what I've got now is the limit as t approaches infinity of the natural log of the absolute value of t. Now that I have simplified, I've took the integral and I've simplified everything that I could here, now I can go ahead and take this limit. Hopefully you guys remember what the natural log function looks like. The natural log function looks something like this. And while it does not go off to infinity very quickly, as x approaches infinity this way, this function still does keep growing. So as t approaches infinity of the natural log of t, this is going to go to positive infinity. And since this approaches positive infinity, which is not a finite value, this is a divergent integral. So the integral from 1 to infinity of 1 over x dx is divergent. It does not approach a finite value. Again, that's a very, very important concept. We'll do plenty more examples. Okay, if we compare the results, however, of 1 to infinity of 1 over x squared dx and the integral from 1 to infinity of 1 over x dx, if you think back to what we did kind of in the beginning of this, 1 over x converged because we did get a finite value of this. And 1 over x diverges. It's very interesting to think about geometrically. Let's take a look at this. So 1 over x squared looks like this. Let me see if I can draw it better this time. Okay, take my time and I can do a little bit better. 1 over x squared looks like this. So again, if we start at 1, and technically we're going off to infinity here. We could put a t way, 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 way out there somewhere, but we're talking about this area right here. This one here is 1 over x squared. So y equals 1 over x squared. According to this actually has a finite value. Okay, we actually found that in the beginning, that this converges. This has a finite value. As a matter of fact, I think we found that the integral of this thing approached 1. 1 over x, which is kind of interesting, in the same area, looks very similar. I'm going to start that over. That's horrible. And I deliberately drew this exactly like I have it there. Again, here's about 1. So the interesting thing here is that this does not have a finite area as we let this thing go off to infinity. And this is y equals 1 over x. The concept behind this, because these two functions look very similar, what you should see is that this one actually is a little bit higher off of the x-axis than this one is. They are both, as they approach infinity, both of these functions are going to approach 0. The problem is that this one right here does not approach 0 fast enough. This one approaches 0 much faster than this one does. So you can actually approach at different rates. This one approaches faster. This one does not approach fast enough, and therefore this one actually does not approach fast enough that we can actually find its finite value where this one does. A very interesting concept. And we've proved it algebraically using the improper integration. All right. Example number 2. We're going to evaluate the integral from negative infinity to 0 of x e to the x dx. All right, this one's going to be a little bit more involved. We're going to still have to use some of our other antiderivative techniques to do these problems. The first thing we're going to do, however, again, is we notice that there's an infinity and a bound. We're going to change it to a finite variable. And this is going to be the limit as t approaches, in this case it was negative infinity, of x e to the x dx. Okay, this is not something that we can take a standard antiderivative of using the power rule. As a matter of fact, we have a power function here and we have an exponential. This looks like it's going to be an integration by parts. So we're going to go ahead and you could do it in either way using integration by parts, or you could actually use the table here and do tabular. It's completely up to you. I'm going to go ahead and do the table. Integration by parts works just fine, but I'm going to go ahead and do the table instead, because one is terminating and the other is cyclical. So this will be x, that'll be e to the x. So taking the derivative of the left is 1, then 0. The antiderivative, fortunately, of the right is very simple. It's just e to the x. We're going to match these things up. Remember that this one stays the same sign, that one changes the sign. Don't have to worry about anything from 0 below. So what I have is the limit as t approaches negative infinity. I've gone ahead and taken my antiderivative by doing this portion, so this will be x e to the x minus e to the x, and I'm going to evaluate that from t to 0. So let's go ahead and plug some of this stuff in. We have the limit as t approaches negative infinity. Plugging in 0, I'm going to get 0 e to the 0 minus e to the 0 minus, plugging in t, we're going to get t e to the t minus e to the t. Now don't forget, e to the 0, anything to the 0 power is 1. This one is going to be 1 times 0, so that's gone, but this is going to be minus 1, so I'm going to get the limit as t approaches negative infinity. And again, I'm always simplifying before I try to take the limit. This will be minus t e to the t, and this will be plus e to the t. Now I can try and evaluate this thing. This is constant. This is negative 1. So as t approaches anything, this is going to be negative 1. Okay, so I'm starting my evaluation process now. So I'm going to get negative 1 out of this first piece right here. The last piece is e to the t. But if I plug in negative infinity or really, really large negative numbers, it's really basically saying e to the negative infinity, which is the same thing as saying 1 over e to the infinity. So this becomes 1 over some huge number. Remember, that's what a negative exponent does. It makes it 1 over something. So this becomes 1 over some huge number. This piece here approaches 0. So it's really this middle piece right here that's going to cause us some issues. This is where the whole idea of L'Hopital's rule is going to come in, and hopefully you guys understand what that is. But if not, again, I'll try and walk you through it just a little bit here. So this piece right here, if I plugged in negative infinity for t, you would basically get some form of infinity times another form of infinity. In this case, this one would actually go to 0. So you'd actually get infinity times 0, because we just did the e to the negative infinity part here, and this approaches 0. So you'd get infinity times 0. It'd be really, really nice to say that infinity times 0 was 0, or infinity times 0 is infinity. We just don't know. This is what is called an indeterminate form. So what we have to do is we have to rewrite this function. We have to put it into a form to use L'Hopital's rule. Let me write this up here. To use L'Hopital's rule, you must get something which is in the form of 0 over 0 or infinity over infinity. Infinity times 0 does not count. So we have to rewrite this so that we can get it that way. So what we can do off to the side here is I can take t e to the t, and I'm going to rewrite it as t over e to the negative t. And I can do that because this negative exponent would bring the e to the t back up to the top. It would still be this function. So I'm just basically taking this and putting it to the bottom, but giving it a negative exponent. So what we can do now is, when you plug in negative infinity in here, what I would get is some form of negative infinity. And if I plug negative infinity in here, it becomes negative of negative infinity, which is positive infinity. E to the positive infinity is infinity. So I do have something now that's in the form of an infinity over an infinity. So this is something I can now use L'Hopital's rule on. If I use L'Hopital's rule, what it says is this. If I take the derivative of the top and the bottom separately and then reapply the limit, it's the same thing as applying the limit in this form, but we might actually get a finite value. So if I use L'Hopital's rule, I'm going to take the derivative of the top, which is 1, and the derivative of e to the negative t on the bottom is negative e to the negative t. And then I'm going to reapply the limit. So if I reapply the limit now, the top is 1. The denominator is going to go to some form of some huge infinite number when I plug negative infinity in, because remember that negative becomes positive. So it's e to some huge positive value. It's just going to be 0. 1 over some astronomically large number is going to go to 0. So ultimately what I get out of this is that this piece goes to 0. And again, if this is something you're not familiar with, I strongly urge you to go try and find this someplace, the L'Hopital's rule. It's a really, really handy thing to use. And if this was just a reminder, then hopefully it's bringing back some stuff as far as using L'Hopital's rule. So ultimately what we get out of this whole thing is that we get -1 plus 0 plus 0. So the whole thing equals -1. And since this is a finite value, this integral is convergent. Okay, the finite value does not have to be positive, it just has to be finite. So after all of this, we get that this integral is convergent. All right, I think that's enough for this video. We will come back with a second video.